Hello everybody, in this video I'm going to give a Stellarium demonstration of the equatorial coordinates so you can see what they look like on the night sky. I have pre-set up Stellarium, so we're going to go directly to a night view instead of the view that we have right now. I'm going to go ahead and make this my full screen. No, don't think you see that on my end, but it'll make things a little bit easier. Okay, let me orient you to when and where we are. Notice I have set the date. We're in July 17th of this year, so we're about a month ago. This is when comet Neowise was viewable in the sky, which you can see right over here. So I have comet Neowise here in Stellarium. And we are looking to the north right now. There is Polaris right there, so we can see Polaris. And let's go ahead and before I turn on the grid system, let's turn on our constellations. All right, just a quick review. Show this every time I can. Here we have the Big Dipper. So our asterism in our constellation figure of Ursa Major. Take these two stars, follow them out, and that'll point towards the North Star Polaris, which sits directly above due north. So here is our north celestial pole on our celestial sphere, which, by the way, if you have not yet watched the video where I introduced the equatorial coordinates and you're having trouble with that by going through just the notes on your own, please go watch that video so you know what I'm talking about whenever I say the north celestial pole and right ascension and declination. So before I get into right ascension and declination, one of the things I do want to demonstrate to you, actually, no, let's just go ahead and turn on the grid. All right, so turning on the equatorial coordinate grid. So this is the analogy of latitude and longitude out onto the celestial sphere. Since I was already talking about Polaris, here we have Polaris. Right here, where all these lines of right ascension and declination converge, would be our north celestial pole, and Polaris sits right by it. So now you can see that instead of the grid that we had before, we're looking at a slanted grid up onto the sky. This is what right ascension and declination looks like projected on the sky, where these lines right here that are going around like this, as I am approaching the north celestial pole, I'm moving up northward on my celestial sphere. So these lines are my lines of declination, and the ones that are wrapping around the east to the west part, these lines right here, are my lines of right ascension. So you can see that here we have 70 degrees, plus 70 degrees declination, plus 75, plus 80, plus 85, plus 90, right at the north celestial pole. And here you might be able to see the hours are indicated. So here's 15 hours, 18 hours, so on and so forth for our lines of right ascension. Let's take a view around, and now you can start to get a sense that you're looking up towards the point of the sphere, the north celestial pole, as we look towards the south. Here would be our celestial equator. Let's go ahead and turn that on. So I'm going to go to my markings and turn on the celestial equator, but I want to make it bright orange for us. Okay, and now we should have a bright orange celestial equator. So there's our celestial equator in bright orange. And moving around, and we can't see the south celestial pole because we're in the northern hemisphere of the Earth, but not allowing us to see all the southern part of the sky. It's just impossible to see from where we are. And here you can see the Milky Way in the background. Now let's go ahead and look straight up so you can see our lines of declination as we move towards the north celestial pole and our lines of right ascension. So far I've had time as frozen. So remember that our equatorial coordinates, our celestial sphere coordinates, are fixed to the celestial sphere. So as the Earth rotates underneath it, what causes the motion in the sky, our grid system should rotate as well, because as the stars are moving, our right ascension and declination should move as well. Let's go ahead and get time moving. So now we can see that the entire coordinate system, right, ascension and declination, are rotating around as time moves forward. We're also seeing that some stars are always just going to rotate around and around and never set, viewable from Knoxville, what we call circumpolar stars. We'll come back to that in a later video. But notice that the right ascension and declination coordinate system stays fixed. And that means that all of these stars are fixed relative to that coordinate system. Every star on here has its own unique address. Going a little bit forward, want to go to the next night. You can see it just spinning around and around the North Celestial Pole. Everything seems to rotate there. Let's go back to where it's a little bit darker. And let's just pick a star. Let's go with Alioth down here. And if I click on it, it brings up a lot of information. Don't get overwhelmed by all the information. All I want to do is I want to check its coordinates. And here we have right ascension and declination. We set that to where everything was in 2000. That's what the J2000 means. And notice that even though time is moving, those coordinates are fixed. Those are that star's address. You could click on a different star, Capella, and it has a fixed right ascension and declination. They do not change. Even if I really ramp up time, they stay fixed. Right ascension and declination, that gives us the star's address. So, as you can see, very useful for locating where things are on the celestial sphere. And now you have a view of what the declination and right ascension system or equatorial coordinates look like when they're projected in the celestial sphere. You're also starting to get a sense of, hey, here's our northern horizon. Our north celestial pole is a fixed altitude above the horizon. We're going to see that that altitude is reflective of our latitude on Earth. So this would be an altitude of 36 degrees for Knoxville. Don't believe me? If I change where I am on Earth, so if I go to a lower latitude on Earth, this should move to a lower altitude. All right, let's actually test that. So let's move down to, say, 20 degrees north. Not 6, 20 degrees north. And now it's closer towards the horizon. As we move towards the equator, it's harder to see the north celestial pole. And I can even switch my coordinate systems. So now you can see that, yes, it's right at about 20 degrees altitude. What would you guess is going to happen if I move this all the way up to the North Pole? And again, we'll simulate polar night. Actually, instead of simulating, let's just go to polar night. And we're looking up, we're looking straight up. And here is Polaris, here at an altitude of 90. So at our zenith point, and we're here at the North Pole. All right, so a little bit of extra information right there. I want to show you that this grid is fixed on the sky. What parts of the grid depend on what latitude we are on Earth. So let's go to minus 35. Doesn't allow me to do that. I want to move this to the south for us. There we go. So let's move this to 35 south. Let's go ahead and turn off the atmosphere. So now we're looking at the south celestial pole. We rotate around. And everything's going to seem to rotate around the south celestial pole if we're in the southern hemisphere. So go ahead and speed up time. Oh, sorry, I'm on the wrong coordinate system. I was about to say that looked like it was the wrong place. There's our south celestial pole. Everything seems to rotate around this south celestial pole. Here we have our lines of Declination are lines of right ascension that are rotating around it, but notice that there's no south star. A little bit harder to navigate. All right, but everything seems to be rotating around that point. So some bonus on top of the bonus. If you have any more questions about right ascension and declination, be sure to post them in the discussion. I know this is a new and rather foreign concept to a lot of you, and it's really hard to wrap your brain around, especially trying to think about what's up, where, and when. That's what we're going to be talking about a little bit later, but you have now been introduced to the basics of how we navigate the night sky.